In the silence of transport crates deep in the savannah, a quiet war begins. Not against predators, but against physics. Moving a lion isn't just about muscle and cage strength. It's about understanding how motion, tension, and stress ripple through a creature designed to dominate terrain, not surrender to it. Each journey, each kilometer, is a calculated negotiation between biology and mechanics. And strangely enough, the answer to moving these apex predators safely doesn't come from veterinary science or safari tradition. It comes from underground, from the same systems used to stabilize the tremors of mining shafts carrying tons of unstable ore hundreds of meters below the surface. In mining, torque calibration is a matter of survival. High-density rock, when shifted too fast, vibrates with destructive force. It destabilizes cables, triggers chain reactions, and threatens entire structures. Replace rock with a sedated leopard, and the logic remains. When transporting predators, every bump, every turn, every vibration becomes a trigger. One spike in lateral movement, just 0.3 G, is enough to activate a full adrenal surge. In sedated animals, that means internal chaos, accelerated heart rates, cortisol flooding the system, and post-release behavior that can spiral toward fatal outcomes. What was once instinct becomes confusion. What should be rest becomes distress. That's why engineers began adapting vibration-damping technologies from industrial lifts to wildlife logistics. Inside these predator crates, high-tension aluminum frames are now reinforced with dynamic tensile dampers. These are not cages. They are precision containment systems. Every bolt is calculated. Every corner is tested. These frames don't just contain mass. They absorb momentum. They turn violent sways into controlled pulses. The kind of engineering that, when scaled down, would go unnoticed, but when scaled up to contain 180 kilos of feline muscle and reflex, becomes a matter of life and death. At the core of this evolution is the fusion between sensors and biology. Embedded in the transport system are real-time accelerometers, the same type used in mining to detect underground quakes. But here, they connect to subdermal biochips inserted into the animals before loading. These chips track stress biomarkers, mapping how motion affects their internal state. What emerges is a neurological map of transport, a visual report of how fear behaves inside a crate. When the movement crosses a threshold, handlers receive alerts. They adjust speed, tilt angles, vibration patterns. The transport becomes responsive. It listens to the animal, not just the road. This isn't luxury. It's logistics guided by neuroscience. Because when a lion trembles in transit, it's not just fear. It's the echo of a system out of sync. And when it arrives stressed, the risk isn't just to the animal. It's to the ecosystem it's being reintroduced to. The entire success of a release operation can hinge on something as small as how a turn was taken on a gravel road. The quieter the crate, the calmer the predator. The calmer the predator, the higher the chance it survives. That's why predator logistics today studies not just claws and sedation, but torque, vibration, and mining physics. In this world, fear has weight, and science knows how to carry it. Before the crate even moves, the first risk has already been triggered. It happens in the enclosure. In the narrow corridor where a lion hesitates, senses confusion, and turns. One wrong movement, one forced push at the wrong angle, and the predator's body enters a state of anaerobic overload. It's a response invisible to the naked eye. No growl, no resistance, just an internal surge of heat, muscle rigidity, and neurological shock. This moment, often dismissed as routine handling, is in fact one of the most dangerous phases of transport. Because the stress it generates doesn't stay in the moment, it follows the animal for hours. Sometimes, it follows for life. To counter this, engineers and behavioral biologists are working side by side to redesign how predators enter their transport chambers. The solution lies not in strength, but in flow. By replacing linear enclosure designs with vestibule-guided entry chambers, structures that use curved walls and optical barriers, the animal's line of sight is softened. There's no visible end, no human figure pressing from behind. Instead, the pathway becomes instinctive, a guided movement, rather than a forced submission. It's not just architecture, it's behavior molded through geometry. And the data is clear. In comparative trials, lions confined using straight-line push techniques showed serum creatine kinase levels 32% higher than those guided through curved vestibules. This enzyme is a marker of muscle trauma, often linked to panic-induced tension and forced restraint. Even when sedation is applied later, the body retains the shock. It remains wired, burning energy it cannot afford to lose. Transport then becomes an extension of that trauma, not a neutral phase. In southern Africa, one wildlife reserve implemented these optical flow chambers into its predator translocation program. The results were not subtle. Chemical sedation requirements dropped by 61%. The animals entered crates with less resistance. Recovery times improved. Mortality during relocation plummeted. It wasn't just about moving animals more humanely. It was about engineering safety through empathy. A lion that walks calmly into a crate lives longer. That's not philosophy. That's logistics backed by biology. Behind every predator capture is a design decision. And the most dangerous ones are those made for human convenience. Straight lines, narrow angles, fast loading. They save time for the crew, but they steal resilience from the animal. The most advanced wildlife engineers now operate under a different principle, one that doesn't center the handler, but the predator. Because the crate is not just a container, it's a biomechanical buffer, and every degree of its shape matters. In this equation, speed is a risk multiplier, but design is a survival tool. And in the world of predator logistics, the safest path is not the shortest, it's the most instinctive. There is a second enemy in predator logistics that travels invisibly, through the skin, beneath the fur, in the slow accumulation of heat. Big cats, even sedated, continue to generate body temperature at a pace that is often underestimated. Their musculature, their metabolic rate, their sheer size all combine into a biological engine that does not switch off. And inside most transport crates, this heat finds no escape. The ventilation systems are often designed for ambient cooling, for general airflow. But the problem isn't in the air, it's where the body touches the floor. Under sedation, thermoregulation changes. The animal no longer adjusts its posture to release heat. It doesn't move to a shaded area or pant for relief. Its body becomes passive, but still radiates warmth. The contact points between skin and crate floor become thermal traps. A subtle localized overheating begins, peripheral at first but quickly spreading. The result is disorientation, internal dehydration, and post-transport confusion. What looks like recovery delay is, in many cases, a thermodynamic failure. The engineering solution came from an unlikely source: horticulture. In high-value agricultural exports, root systems are kept alive during long-distance travel, using passive phase-change gel linings. These linings activate at precise temperatures, absorbing heat without the need for fans or mechanical cooling. When this same principle was applied beneath predator crates, the transformation was immediate. By embedding gel layers calibrated to activate at 38.5 degrees Celsius, engineers created a passive subcutaneous cooling system. It doesn't blow air. It doesn't require power. It simply responds to the animal's own temperature. And it works exactly where it matters most, at the point of contact. In field studies, crates equipped with this system showed a 27% reduction in post-transport behavioral irregularities linked to thermal stress. Fewer signs of confusion, faster recovery orientation, lower incidence of pacing or post-sedation aggression. These aren't just improvements in comfort, they're enhancements in survivability. Because when a lion wakes in the wild after a long journey, seconds matter. Clarity matters. Confusion can mean failure. And failure, in these contexts, means loss of life or recapture. In Botswana, a specialized wildlife transport firm integrated this cooling solution across its fleet. The impact was direct and measurable. Sedation dosages were cut by 30%. This meant fewer side effects, more consistent awakenings, and reduced time under risk. It also meant that the crate became more than a container. It became an extension of biological intelligence, a structure that didn't just hold the animal, but interacted with it, silently, precisely, reliably. Predator logistics is often thought of as a matter of strength, of reinforcement, of restraint. But this chapter reveals something different, that the real challenge is not brute control, but subtle engineering. That survival can hinge not on what surrounds the animal, but on what touches it. And that temperature, in this world, is not an ambient reading. It's a point of contact problem, solved not with complexity, but with elegance, through the quiet brilliance of thermodynamics at the service of life. To understand the future of predator logistics, one must look not to the savannah or the research lab, but to an unexpected place, the industrial corridors of poultry plants in southern Brazil. Here thousands of chickens pass through conveyor systems every hour, each one a fragile structure of bones, organs, and reflexes, and yet breakage is rare. Fractures are minimized. Cardiac stress is systematically reduced, not through sedation, not through restraint, but through mechanical design that learns from biology. What these poultry systems achieve in microseconds, predator transport must now achieve at macro scale. Because the principles are the same, the mass changes, the risk changes, but the body still listens to vibration, and the mind still reacts to motion. In these poultry systems, every detail is controlled: the angle of the platform, the duration of a tilt, the spacing between vibrational pulses, not arbitrarily but based on biomechanical feedback, studies of wing tension, heart rate, and muscular strain. These systems know how to move animals that cannot speak, cannot resist, and cannot prepare. They move them in rhythm, a rhythm that reduces trauma. And this is not just about minimizing harm, it's about maximizing life. In the same way, when we transport lions, leopards, or other apex predators across hundreds of kilometers, every bump becomes a signal. Every vibration is interpreted by the animal's nervous system. The difference is that for a predator, the cost of misunderstanding that signal can be lethal. The transition from poultry logic to predator transport is not literal, it is adaptive. The question is, what happens when we scale that same logic from grams to hundreds of kilograms? In Australia, a pioneering logistics project decided to find out. Drawing directly from the architecture of poultry conveyors, they reimagined the way large predators are moved across protected zones. The platform wasn't a standard steel trailer. It was a stabilized rail bed mounted on silent roll bearings, originally used in delicate food handling systems. The lift angles were reduced. The entry ramp was extended to prevent sudden posture shifts. Shock absorbers were recalibrated not for mass, but for vibrational frequency, targeting the range most likely to activate neurochemical stress in sedated felines. The impact of this design shift was measurable. Transport-related trauma, classified by post-release disorientation, abnormal pacing, vocal strain, and muscle inflammation, was reduced by 45% across multiple cases. No increase in sedation, no additional restraint, just a mechanical system that moved differently, that responded to biology, rather than simply enclosing it. This was not luxury, it was efficiency through precision, and it reframed how we think about logistics, not as the art of moving things from one point to another, but as the discipline of preserving function through every phase of movement. The most revealing insights came at the final transition, the moment between ramp and crate, or crate and open habitat. These are moments often overlooked, yet in biomechanical terms they are critical. As sedation fades and the predator begins to regain autonomy, its body is vulnerable. The spinal column adjusts, reflexes reawaken. If the exit angle is too steep, even by a few degrees, the animal may brace incorrectly, leading to cervical strain, throat bruising, or even microfractures in muscle attachments. These injuries are rarely visible at the moment. They appear later, in reduced aggression, disrupted feeding patterns, or altered gait. And because they don't bleed, they often go unaddressed. Yet their source lies in something as simple as a misaligned ramp or a poorly distributed weight shift. Brazilian conveyor logic solves this in poultry systems through subtle modulation, slight pauses, leveling platforms, and feedback-driven vibrations that recalibrate based on load. Predator logistics, by adopting the same sensitivity, begins to treat its subjects not as cargo, but as dynamic biological systems. That shift, from mass to living system, is at the heart of what comes next. Because ultimately, predator logistics is not about building stronger cages. It's about designing systems that align with the animal's physiology, not overpower it, that recognize the nervous system as part of the cargo, that treat the heartbeat as a parameter in mechanical design. This is the frontier where engineering meets life science, where logistics becomes orchestration, and where movement is no longer defined by horsepower, but by pulse synchronization. It's here that we see the future. Machines that don't dominate, but adapt. Platforms that don't just transport, but translate biology into motion. And handlers that understand, moving a predator safely doesn't begin with containment. It begins with listening, to pressure, to rhythm, to stress, to life.